Backed by popular demand, we get a little bit more on IR spectroscopy. When we ended that last video, you were looking at going from the spectra to structure. So now let's take a look at the reverse. Let's do the structure to the spectra. So if you're given the structure, you have a big advantage here. You now have a whole bunch of different pieces that you could look at. So when you look at IR spectroscopy, remember what it's trying to identify. And you'll hear a bunch of variations of this, but really when you hear IR spectroscopy, the only thing that I want to come into your head is bond. Okay? Not functional group. Everybody says functional group, and it's half right. Stick with bonds. So if you're trying to go from the structure to the spectra, what you need to do is identify the bonds that show up within the structure. So I'm going to attempt to color code this. We'll call this one, our first one, red. Within this structure, I see carbon-carbon double bond, carbon-hydrogen, okay, OH, and at that point, and we have CO. Hopefully what you recognize is this CH is a little bit tricky because we have CH out here and we also have CH in here. Those two types of CH are different. Okay? They're different because the carbon part of that structure has a different hybridization, which means the chemistry of that carbon also changes, which means the bond changes and it shows up slightly differently. So when we look at CH, you should also specify that it's sp3 hybridized, and technically we also have a CH that is sp2 hybridized. That extra information is important when trying to evaluate your structure. One of the bonds that I did leave off, almost intentionally, would be a carbon-carbon single bond. This is one that you will see me never write down after this because the carbon-carbon single bond shows up in the fingerprint region. Too difficult to interpret, so don't worry about it. Okay. We move to the next structure, which we'll call structure number 2 in purple. We would again evaluate. I've got carbon-hydrogen, where all of my carbons are sp3 hybridized. I've got an OH, and I have a CO. Alright, so I've again identified all of the bonds within that structure. Next one we'll call structure 3. I see an OH, carbon-oxygen double bond, carbon-oxygen single bond, and a CH, again, sp3 hybridized. Alright, so again, we're just listing out all of the bonds that are present. We'll address how we can use this information in a little bit. Last one we'll call 4. We have an NH, CN, and a CH, sp3. This is a point that I want to address here. A lot of people, particularly if you're getting help from others, might call this ring a benzene. It is not benzene, okay? It's also beside the point. Benzene is a functional group or a larger structure. IR doesn't tell you anything about the larger structure. What it tells you about is the bonds. The bonds present in this structure are carbon-carbon single bonds and carbon-hydrogen sp3 bonds. Okay? Go through and look up benzene. This is not benzene. It's not going to give you that same relationship. Okay? Now that we've identified all of the bonds that we see in this, we can now try and propagate this out because maybe we don't care about some of these bonds. So what I would go through and do is now compare these 4 structures. And these 4 structures should look familiar to you, particularly if you've been working on that IR lab assignment. Okay? I see CH-sp3s in all of these. Okay? To me, that means useless. So I'm going to go ahead and erase those. Okay? Why would they be useless? Well, they all have CH-sp3s. That's not going to help me at all because all of those would show it. So that's not going to be very useful. I happen to erase the wrong one up in our red one, so we'll just tweak that red one a little bit, make that an sp2. Okay. The CH-sp2, interestingly enough, since we're there, only one structure has that. So that I would mark off as a very characteristic feature. So if I only had 4 spectra to look at, I would look for that CH-sp2 because that's going to tell me that's structure 1. None of the other ones have that characteristic. I have my answer. I don't have to worry about the rest of the spectrum. Okay? Other things that we could try and look for. You'll notice that OHs show up in 3 of these. Okay, so the OH, while it's a nice characteristic bond, 3 of them have it, so that's not the easiest thing to pick out in the IR because all 3 have it. But we could go through and say that our NH was different from that. Okay, well, the NH is different from that, but if we look up the NH bond in your table of example pictures, the ones that are shown are sharp, but if you read about them, they sometimes say they're broad. We'll talk about that difference in just a little bit. The primary issue with that is that if we have an NH that's secondary, meaning it's attached to 2 carbons, we only get 1 peak, very similar to an OH. So while the NH signal would be a good thing to kind of use to pick out away from the rest of these structures, it becomes a little bit more challenging because it looks similar to the OH. Really what we're trying to say is the NH is going to be different if you read more about them. They're a little bit less intense than the alcohol. So we could look for a signal that looks similar to the alcohol, but much, much less intense. So that could potentially help us identify that structure. Other bonds that we could go through and look at, you'll notice the carbon-oxygen shows up very similarly in all of these, or in 3 of them. So I would erase that from our pattern. We could go through and look at the CN, but just like the CO, it shows up in the fingerprint region, it's not particularly helpful. So really the only way we could identify structure 4 from the others would be looking for that NH bond. The OH, evaluating the difference between each of these. The OH on its own gives you this nice characteristic broad signal. But if we put that OH near, say, another functional group, a carbonyl, we change the characteristics enough that that signal shows up slightly differently. The OH in that blue circumstance ends up being lower wave numbers. So I think the wave number is just a bar, a lower wave number than our standard. So we could go through and look for an OH type signal that shows up lower than where we would normally see it in that 3300 range. Okay? I would still argue that our OH is not the most helpful to look at, because if we take a look again at that same structure 3, we have a carbon-oxygen double bond that shows up unique to only that structure. So again, I would go through the spectra and find something that matched the shape of a carbon-oxygen double bond. If I found it, I've now identified 3. So at best, I've eliminated, well actually at this point, I've eliminated 3 of the 4. The last answer has to be structure 2. Okay? There is no other option. Once you've identified what structure belongs to the IR, then you can go through and label the IR spectrum in more detail and account for all of the individual, or at least 2 of the individual bonds that show up within it. Okay? So take advantage of your structural understanding to identify bonds, then look up what those bonds are supposed to look like, then look at those images within your spectra. Okay? So the last thing we'll go through and talk about here would be the example spectra that I gave you. One thing that one of your astute classmates noted was that on the OH stretch, which is our broad one in the lower left corner, you'll see that there's a number on the what is that, y-axis that might lead you to think more about the intensity. Ignore those numbers. Okay? The scale is all relative on the y-axis. The x-axis is not relative. Those are perfect. You can deal with those numbers. But the y-axis, ignore those numbers, which makes it more difficult with the version I gave you to interpret intensities. The intensities tend to be very relative to each other. Guys, that's what I'm trying to state at the bottom here. So when you look at a spectrum, a full spectrum, and you see something that you think is an OH, it should be of equal intensity or greater intensity than most of the other signals. Okay? If it is lower in intensity than most of the other signals, that should be a big tip-off that you probably are not looking at an OH. And you notice I said probably. There's no guarantee. Okay? IR is a very fast, quick interpretation. We don't get into it super heavy. We use it to give us a good starting point and idea to identify our structures and move forward. Everything you'll see in this class should nail down very, very quickly. Okay? Next big thing to note would be the term broad. Okay? Broad or narrow peaks. In particular, you take a look at the NH. The NH example that I gave you showed two very sharp peaks. Okay? The reason that I used that example is that's the one I had. Okay? So I had to work with that. Unfortunately, both the NH signal and the OH have some interesting properties behind them. They have the ability to hydrogen bond. If we have a hydrogen bonding interaction, the signal gets broader. If there is very little hydrogen bonding, the signal gets sharper. So in the case for the one I provided for you, that NH shows very sharp peaks. Well, that's because it just so happens in the compound that I had used, we didn't get any hydrogen bonding, or we got very minimal hydrogen bonding. Conversely, if you take a look at the OH in the sapling homework, there's at least one problem in the sapling homework that shows OHs that are very, very narrow. Well, that OH can get narrower if there's minimal hydrogen bonding. How do you know if there's hydrogen bonding or not? How broad is the peak? There really isn't anything beyond that. Okay. Thankfully, as far as you guys are concerned, in that 3,500 range, there's really only OHs and NHs. So if you see something there, regardless of broad or narrow, it's going to be one of those two. If it's intense, OH. If it's weak, you're probably looking at NH. Okay? Same idea kind of applies in all of our other sections. I did kind of outline these. We're looking at our CHs, the CO, our CC double bonds, and then sometimes see, the carbon-oxygen single bond. Okay? Hopefully that kind of clarifies the idea when you look at these. Ultimately, you're going to need to look at more and more spectra. So you've got the 10 examples that I gave you in the IR assignment, and then you have probably another 5 or 6 spectra in the sapling. Your textbook's going to have a ton more. Use your textbook. The answer's at the back of the book, I think. Use that to kind of compare and match through. And worst case, you try twice, send me an email. Okay? If you're still getting something wrong, you are missing something. And you need to find help, either through a tutor or through me. Okay? So please take advantage of my help. I will try and be around as much as I can, and I will be checking my email fairly frequently. Thanks for listening, and good luck.